Ever wonder how those tiny chips that power our smartphones and self-driving cars are made?
Yeah.
Well, get this.
Duh.
One of the biggest challenges is keeping them totally dry
Yeah.
during manufacturing.
It's true.
Today, we're deep diving into the world of semiconductor fabrication
Okay.
to learn how the industry tackles moisture.
Yeah, we're talking about a level of precision where
Yes.
even the tiniest bit of moisture can completely ruin
Wow.
a whole batch of chips.
So let's talk about the heart of the problem.
Mm.
These specialized containers called FOUPs.
Okay.
They're like high-tech suitcases for carrying around the silicon wafers that chips are built on.
Uh-huh.
And we have a research study from the International Journal of Thermofluids
Okay.
that dives into how engineers are fighting moisture.
It's a constant battle.
Yeah.
These FOUPs are designed to be super protective,
Okay.
but they're not completely airtight.
Right.
They need to be open to load and unload the wafers.
Yeah.
And that's where things get tricky.
Okay, so every time you open a FOUP, you're basically risking a moisture invasion.
Exactly.
So what are some of the strategies that they're using to combat that?
Well, think of it like this. They're essentially creating a tiny controlled atmosphere
Okay.
inside these FOUPs.
Mm-hmm.
One method is gas purging,
Okay.
where they use a constant flow of clean, dry air,
Right.
almost like a gentle breeze,
Oh, okay.
to push out any moisture.
So it's like they're constantly giving the FOUP a little blow dry.
Exactly. And they've also got another trick up their sleeve,
Okay.
laminar air curtains.
Mhm.
Imagine a shield of downward flowing air acting as a barrier,
Huh.
preventing any stray moisture from sneaking in
Right.
when the FOUP is open.
Interesting.
Yeah.
So it's like a combination of pushing the moisture out
Yeah.
and creating a barrier to keep it from coming back in.
Exactly.
What I find fascinating is that these researchers actually visualize the airflow
Yes.
inside these FOUPs
Yeah.
using lasers and smoke.
They used a technique called particle image velocimetry,
Wow.
or PIV,
Okay.
to create these incredibly detailed maps
Uh-huh.
of how air moves inside the FOUP.
So they could see how effective
Right.
these different moisture control methods were.
Yeah, it's like watching a tiny weather system unfold,
Wow.
but for dry air fighting moisture.
So with those visualizations, did they find a clear winner?
They did. One of the key findings was that a special tube called a diffuser,
Okay.
which helps distribute the dry air more evenly
Right.
during purging,
Hmm.
significantly outperformed conventional methods.
Interesting.
It's like having a shower head for dry air,
Okay.
ensuring every nook and cranny of the FOUP gets that dry airflow.
So diffuser purging is the way to go.
It seems so.
Okay.
But here's where it gets even more interesting.
Okay.
They found that combining the diffuser purge with the laminar air curtain
Uh-huh.
created the ultimate moisture-busting combo.
Wow.
It resulted in the lowest humidity levels by far.
Okay, so we've got this dynamic duo.
Yeah.
A constant stream of dry air being strategically distributed.
Right.
And a shield guarding the entrance.
Exactly.
I'm starting to understand how seriously they take moisture control.
Absolutely. Remember, we're talking about incredibly sensitive components here.
Right.
Even a tiny amount of moisture can cause huge problems.
So I'm guessing this isn't just about keeping things tidy.
No.
What are the real-world consequences?
Well, imagine those tiny circuits on a microchip being disrupted by microscopic water droplets.
Ah.
It can lead to all sorts of defects,
Right.
causing malfunctions or reducing the quality and lifespan of the chip.
Oh, so it's not just a matter of a slightly wonky chip.
Right.
We're talking about potentially impacting the performance of our devices.
Exactly. And considering how reliant we are on these chips
Right.
in our smartphones, cars, medical devices,
Okay.
even a small increase in defects can have a ripple effect.
Wow. I'm starting to see the bigger picture here.
Yeah.
This seemingly niche topic of moisture control in FOUPs
Right.
is actually connected to the reliability and performance of the technology we use every day.
It's a perfect example of how something we take for granted,
Right.
dry electronics, is the result of meticulous engineering
Uh-huh.
and a constant battle against an invisible enemy, moisture.
This has been an eye-opening start to our deep dive.
Yeah.
We've gone from specialized containers to lasers and smoke.
It's a whole world in there.
And it's clear that there's a whole lot more to uncover
Indeed.
about the intricate world of moisture control in semiconductor manufacturing.
And what's even more fascinating is that this research raises some interesting questions
Okay.
about the real-world application of these techniques and what challenges lie ahead.
All right, now I'm really intrigued.
Okay.
We'll be back shortly to dive into those real-world challenges
Sounds good.
and the potential implications for the future of chip making.
Welcome back.
I am eager to dig into some of the specifics of how the researchers simulated real-world conditions
Yeah.
in this study.
Yeah, it gets pretty clever.
Yeah, that was one of the things that really jumped out at me. They built this whole mini environment to mimic the conditions
Right.
inside a real semiconductor fabrication facility.
Yeah.
I'm picturing a tiny little factory complete with microscopic workers.
Well, not quite that tiny,
Okay.
but they did go to great lengths to replicate the airflow you'd find in a
Right.
typical fab.
Uh-huh.
Remember those large fan filter units, or FFUs we mentioned earlier?
Yeah.
The ones that constantly circulate clean air
Right. In a
in
clean
your room? Well, the researchers incorporated those into their experimental setup.
Makes sense.
Yeah,
But those FFUs, even though they're using clean air,
right.
that air isn't perfectly dry, right?
Exactly.
Yeah.
That's a key point.
Okay.
Standard clean room air still has a relative humidity of around 45%.
Wow.
So even with those systems working,
Yeah.
there's a base level of moisture that engineers are constantly battling.
So even in these super controlled environments,
Uh-huh.
moisture's like a sneaky ninja,
That's a great way to put it.
always trying to find a way in.
And it's not just about the moisture itself.
Okay.
Remember, moisture and particles often go hand in hand.
Right.
Moisture can make those tiny particles stickier,
Yeah.
making them even harder to remove.
Right. So it's like a double whammy.
Yeah,
Moisture not only poses a direct threat,
right.
but also makes those other contaminants more troublesome.
Exactly.
And in this study, the researchers were specifically looking at FOUPs
Yeah.
in an open door condition,
Uh-huh.
which I imagine adds a whole new layer of vulnerability.
Absolutely. Those FOUPs have to be open to load and unload the wafers.
Right.
And even for a short time, that open door creates a prime opportunity
Yeah.
for moisture to sneak in.
Okay, so they're testing these moisture control methods under the most challenging conditions.
Right.
What did they find? Did those diffuser purges and air curtains hold up?
They did for the most part.
Okay.
The results were impressive, especially when they combined the diffuser purge with the laminar air curtain.
Right.
They were able to maintain incredibly low humidity levels,
Okay.
even with the FOUP door open.
So even in that vulnerable moment when the door's open,
Right.
this moisture-busting combo was able to keep things dry.
Exactly.
But I bet they didn't stop there.
No.
I have a feeling these researchers were looking to really push the limits.
You're right.
Yeah.
They wanted to see how these systems would perform under less ideal conditions.
Okay.
Because let's face it, in a real-world fab, things aren't always perfect.
Of course, you've got equipment people moving around. It's a dynamic environment.
Exactly.
I'm sure there are variations in airflow all the time.
So they decided to create a scenario
Well.
where the airflow from those FFUs,
Right.
those big fan filter units, wasn't perfectly uniform.
Okay.
They actually simulated a situation with only 75% FFU coverage,
Wow.
essentially creating a weaker spot
Okay.
in the airflow.
So they intentionally made things a bit tougher to see how those moisture control methods would hold up.
Exactly.
That's smart. Did they pass the test?
They did surprisingly well.
Okay.
Even with the reduced airflow, the diffuser purge, again combined with that laminar air curtain, continued to outperform the other methods.
So even when things weren't perfect,
Right.
this dynamic duo still came out on top.
It really is.
That's reassuring.
It suggests that these methods are robust enough to handle some real-world variations and inconsistencies.
Okay.
But here's the truly intriguing part.
Okay, you've got me on the edge of my seat.
Okay.
What is it?
Even with these highly effective methods in place, the researchers noticed that some moisture still managed to find its way into the FOUP.
Now that's interesting.
Yeah.
If the airflow control was so good, how was moisture still getting in?
Right.
Are FOUPs just inherently leaky?
It's not so much about leaks in the traditional sense.
Okay.
The researchers came up with two interesting theories. The first has to do with the material the FOUP is made from polycarbonate.
Okay.
It turns out polycarbonate is a hygroscopic material.
Hygroscopic. Okay, well, remind me what that means.
Hygroscopic means it tends to absorb moisture from the surrounding air.
Okay.
So even if you manage to push out all the existing moisture, the FOUP itself could be slowly re-releasing some of it back into the interior.
Ah, I see.
Yeah.
It's almost like a sponge constantly absorbing and releasing moisture.
That's a really important insight.
That's a curveball I didn't expect.
It's like trying to dry out a damp towel in a humid bathroom.
Yeah.
You might get it mostly dry,
Right.
but it's just going to keep absorbing moisture from the air.
So even with these fancy airflow systems,
Right.
the very container itself could be working against them.
Exactly.
It makes you wonder if there are other materials,
Yeah.
less moisture-absorbing materials that could be used for FOUPs.
That's a great point, and one that the researchers themselves raised. They suggested that exploring non-hygroscopic materials for FOUPs could be a valuable area for future research.
Right.
Imagine a FOUP that actually repels moisture.
That would be a game changer.
Yeah.
It seems like even in a field as advanced as semiconductor manufacturing, there's always room for innovation and new discoveries.
Absolutely.
And their second theory about moisture intrusion is even more surprising.
Okay.
It involves the laminar air curtain itself.
Oh.
What, the air curtain?
Yeah.
I thought that was supposed to be the shield, the protector against moisture.
Right.
How could it be a source of the problem?
It's not that the air curtain itself is moist.
Okay.
Remember, it's using clean, dry air.
Right.
But because of the way the LAC device is designed, there's a small gap around the edges of the outlet panel where the air flows out.
So there's this tiny unintended opening around the edges of the shield, just big enough for a few sneaky moisture molecules to slip through.
Exactly. And the researchers believe that humid air from the surrounding environment might be finding its way into the FOUP through those gaps.
Wow.
It's a subtle flaw, but at the microscopic scale we're talking about, even a tiny amount of moisture intrusion can be problematic.
It's amazing how something so seemingly insignificant, a tiny design flaw, can have such a big impact.
Exactly.
It really highlights the incredible attention to detail required in this industry.
It really does.
Every aspect of the process, from the materials used to the design of the equipment, has to be meticulously considered and controlled.
It's like building a house of cards in a windstorm.
A very high-tech house of cards indeed.
Right.
This has been a fascinating deep dive so far.
It has been a fascinating
deep dive. We've gone from lasers and smoke to hygroscopic materials and tiny design flaws. And it all underscores the incredible complexity of semiconductor manufacturing and the lengths they go to in order to create those tiny, powerful chips that are so essential to our modern world.
And there's still more to explore.
Right. We still need to talk about what all of this means
for
the future of semiconductor manufacturing.
Indeed. We'll be back in a moment to discuss the implications of this research and explore some of the questions it raises about the ongoing quest for cleaner, drier, and more efficient chip production.
All right. Stay tuned.
Welcome back to our deep dive into the world of moisture control and semiconductor manufacturing. We've uncovered some fascinating insights about how they keep those tiny chips dry
it's quite a project.
and functioning properly.
Absolutely.
But now I'm really curious about the so what. How will all of this research actually impact the future of chip making?
That's the million-dollar question.
Right.
This research has the potential to lead to some real-world improvements. First and foremost, it demonstrates the effectiveness of diffuser purging, particularly when combined with a laminar air curtain. So should we expect to see those techniques become the standard in semiconductor fabs?
Well,
I can almost picture rows and rows of FOUPs, each with its own little air shield and a tiny dry air blower.
It's certainly a possibility. But remember, it's not as simple as just flipping a switch. There are practical considerations like cost and complexity and potential impacts on the overall manufacturing process. Scaling things up from a lab setting to a massive production facility is a whole other challenge.
It's one thing to prove something works in a controlled environment. But quite another to implement it on a large scale.
Exactly.
So what are some of the hurdles they might face?
Well, imagine trying to retrofit existing factories with these new systems. It could require significant changes to the infrastructure and workflow. And of course, there's the cost factor. Implementing these systems across an entire facility would require a significant investment.
So it's a balancing act between the potential benefits of improved moisture control and the practical realities of implementation.
Exactly.
But even if we don't see an immediate industry-wide shift, this research still has a lot to offer, right?
Absolutely. It provides valuable knowledge that can be applied in various ways. Take the discovery about the hygroscopic nature of the FOUP material. That opens up a whole new avenue for exploration.
You're talking about finding alternative materials
Right.
that don't absorb moisture as readily.
Exactly.
I'm imagining a FOUP made of some super advanced moisture-repelling material.
It could be a new type of polymer,
Ah.
a special coating,
Okay.
or even a completely different old-fashioned approach to FOUP design.
And think about the implications for reducing those tiny gaps in airflow.
Right.
Those sneaky openings that let moisture in.
Precisely, this knowledge could lead to improvements in the design of laminar air curtains, FOUPs, and even the layout of the fabs themselves. They could use computer simulations to optimize airflow and minimize those vulnerable areas.
So it's about creating a fortress against moisture down to the smallest detail.
Exactly. And remember, moisture control isn't just about dryness. It's also about reducing particle contamination, which is another huge concern in semiconductor manufacturing.
So improvements in moisture control could have a ripple effect, leading to cleaner chips overall.
Exactly.
It's a win-win.
It is.
And this research aligns with the broader trend in the industry, right? As chips get smaller and more complex, the need for precision and control over contamination only increases.
Precisely. It's like that analogy we used earlier, beating a house of cards.
Yeah.
But now imagine those cards getting smaller and more delicate with each new generation of chips.
The margin for error gets smaller and smaller.
Absolutely.
So in a way, this research is not just about moisture control.
Yeah.
It's about contributing to a deeper understanding of contamination.
Right.
And the importance of meticulous engineering in this incredibly complex field.
That's a great way to put it.
Yeah.
And for our listeners, the takeaway is this.
Okay.
The next time you use your smartphone computer or any piece of technology, remember those countless tiny chips working behind the scenes?
Yeah.
And the extraordinary lengths engineers go to in order to keep them dry clean and functioning flawlessly.
It's amazing.
It's a testament to human ingenuity and a constant pursuit of perfection.
It's amazing how something we rarely think about, moisture, plays such a pivotal role in the story of our technological world.
It just goes to show there's always more to learn, even about the things we take for granted.
That's the beauty of a good deep dive.
It is.
Thanks for joining us on this exploration of moisture control in semiconductor manufacturing.
It was my pleasure.
Until next time, stay curious.